As part of the Science Foundation Ireland Zero Emissions Challenge, CMINUS is a project between the Bernal Institute at the University of Limerick and NUI Galway. The goal is to create smart growing units that will provide the plants with everything they need to thrive, including water and carbon dioxide.
So in the CMINUS project, we're trying to produce food almost anywhere in the world, independent of the availability of water in those locations. So the idea is that we can pull water vapour out of the air and use that to irrigate the plants, even in a very arid environment.
How close are we actually to doing that, being able to pull water and CO2 out of the air?
Well, actually, we're very close to being able to achieve that because partners in University of Limerick and Professor Mike Zaworotko's team have actually developed in the lab these new materials which can take out CO2 and water from the air at extremely low concentrations.
The key components of the project are two new materials, one that absorbs water and the other that absorbs CO2 out of the air. These were developed by Professor Michael Zaworotko and his team at the Bernal Institute at the University of Limerick. Could you explain to a social scientist what is a sorbent material?
Yes, Trevor. So you can think of it like a sponge. A sponge will pick up water, and if you squeeze it, it will release it. In the case of a sorbent material, you don't squeeze it. You apply heat or vacuum. But then you have to release the compound that you're capturing. And that's where the problem lies, because that's where the energy is needed. So the goal here is to make a regeneration optimized sorbent, which requires as little energy as possible to recover the sorbent and release the substance that we captured.
Was it a case that you had a eureka moment with this material?
In my case, it was around about a 40-year journey.
Okay.
The moment we discovered the first ROS material, regeneration optimized sorbent, it was a eureka moment. But it was only through systematic and steady studying and slowly building upon what we learned previously that we made a breakthrough. And in our case, the first ROS material, we were 100% better performance than any previous sorbent material for carbon capture. And this was 2013. We subsequently are into second and third generation ROS materials. So that's what we're using in the CMINUS project. Our current experiments suggest we can do 20 to 30 liters of water per kilogram of material per day under the driest of conditions. So in the middle of the desert, we could capture 20 to 30 liters of water per day per kilogram. The existing technology can do maybe 10. But on top of that, there's the heat needed to recover. So that's the second big parameter. And our materials work at 60 degrees, whereas the existing materials work at well above 100 degrees. So we've got a winner on both counts, which is the amount of water we can capture and the energy needed to recover the material and release the water that we capture.
Hydroponic systems are currently used to grow food, but they need a huge amount of energy to operate.
So a large part of that energy footprint is actually down to the cooling and the dehumidification in these systems. You've got a huge amount of lighting and lots of water vapour coming out into these closed environments, and so we need to remove that water. And that's where these sorbents can be very useful. These new materials can be very useful because they can pull out the water with a very low energy demand compared with conventional dehumidification, as well as potentially providing an input of water from the air for the irrigation to start with in very dry environments. Another efficiency we get with these new materials is that we can take CO2 out of the atmosphere and concentrate it and then increase the concentration of CO2 where the plants are growing. So this means we get much faster growing plants. And now in this project, we're working on scaling that up and putting them into these big rotor wheels, which will be attached onto the shipping container here, and then we'll be taking out the water and the CO2 to put into the plant growing area.
So we're really excited by these materials, these sorbents. What we can do with them is to connect them to ongoing work we have here, which is to develop a smart container farming system for horticultural crops. Using our sensors, we're collecting a myriad of different data in real time. So we're collecting things like the temperature, the humidity, the lighting regimes. So we can integrate all of that data to optimize how plants grow. And that means we can then adjust those environments to meet the plant's needs. So if we feel that the plant needs more of this or less of this, then we can adjust the plant's environment and optimize how the plant grows to ultimately produce more plant per unit time and area.
And what sort of crops do you foresee we will be growing in container?
The types of crops that are currently grown in indoor container systems are largely horticultural crops, leafy vegetables like lettuces, and also tomatoes are a high-value crops, herbs and so forth. There's other crops that make a lot more sense to be grown outdoors rather than in enclosed, controlled environment chambers. However, one of the attributes of this as well is that you can disconnect the farming system from the seasonality aspects, so we can mimic environments within these chambers that allow you to grow crops all year round.
What is the advantage of growing food in this way, in a container?
In countries like Ireland, we import most of our fresh fruit and vegetables, and many other parts of the world, you simply can't produce that food because the environment's not suitable. So the idea is that we can start growing food exactly where we need it and therefore avoid very long distance transport.
Lettuce seems to be the thing we go to, like it is mostly water. We use a lot of it, it goes off very quickly, and it comes from maybe thousands of miles.
Exactly, and it's not just the food miles, so that can contribute quite a lot to the carbon footprint, for example, but the places these things are grown are often in water-stressed areas, so we've got a massive use of water. Just one lettuce can require up to 14 litres of water to produce, so we can massively reduce that down to a fraction of 1 litre of water in a system like this. So we've got big savings for water, for herbicides, pesticides, all the chemicals that are used in open field lettuce production. We avoid soil degradation, and of course we can really spare quite a lot of land, because by having multiple tiers we can actually produce much more per square metre of land that we use with these shipping containers. So potentially we can grow about 50 times more food than we could otherwise grow on the same area of land.
The possibilities of what you can grow, where you can grow it, when you can grow it, just feels like incredible.
Yes, the goal here is, and the irony is not just providing food where it is short, but also changing the way food is produced. So farmland can become forest. You can grow the food, the fresh produce in the cities, not grow them on the farms. So this is where the economic modeling and costing comes in. How much do you really save if you no longer have to devote so much land to farming, and then simply release that land back to its original natural state?
When you start thinking about the huge quantities of fruit and veg that we consume, and when you scale that up and when you think about where a lot of this fruit and veg comes from, we actually have massive environmental impacts associated with some of those production systems because of water depletion. That's going to get worse in the future with climate change. We know that we have to change the way that we live in order to make things, and the way that we produce our food and the way that we travel, to make things more sustainable. So we just need to find ways that we can reduce the inputs and emissions associated with producing things in different ways, so that we can live sustainably ourselves and we can pass the planet on to the next generations in the way that it was passed down to us.